covered linear functions, we've covered quadratic functions. So what happens when our degree is higher than a 2? Well, we have to get into the world of solving polynomial equations. So getting into other higher degrees of polynomials, okay? So the first part of this is a little bit of review, hopefully. We're going to talk about the behavior of different types of polynomials with higher degrees other than 1 and 2. If I have a degree of 1, what does my graph look like? It's just a straight line, right? Okay, so maybe something like this. This would be an a being positive or negative. Your leading coefficient. This would be positive, right? And this would be negative, would have a negative slope, right? Okay, so there's our degree of 1. If we had a degree of 2, degree of 2, with a being positive, what would that graph look like? Concave up. And then a being negative, it would be concave down, right? And we've talked about odd and even graphs, so we kind of already know the behaviors of those different types of graphs. Okay, so let's go ahead and get some vocabulary into the mix here so we all understand this. So again, if this is something you feel like you got, don't feel free to write it down, or write it down if you want. So if we have a polynomial, we're going to use this function as our example. So if I had the polynomial f of x is equal to 3x to the third minus 2x squared plus 5x to the fourth minus x plus 7. And I was using the word term. So if I said to you, how many terms does that polynomial have? Well, what is a term? A term is each monomial in the sum. So out of that polynomial, how many terms do we have? So monomial doesn't have any adding or subtracting. So we would have 1, 2, 3, 4. We would have 5 total terms, right? So for this one, for the example, we would have 5 terms. So each monomial is separated by either a positive or a negative, a plus or a minus. Okay, so terms, we got our term, each monomial in the sum. Next definition is standard form. If you are asked to write a polynomial in standard form, I would hope you guys would already know how to do it because we've kind of done it already. Standard form is when your terms of the polynomial are written in descending degree. So you put your largest degree, fizzle it down to your smallest degree. So if you're asked to put something in standard form, highest degree first, fizzle it down to your smallest degree. So in this case, in my polynomial, my highest degree looks like it is an exponent of 4. So for this example, in standard form would be, so f of x is equal to 5x to the fourth plus 3x to the third minus 2x squared minus x plus 7. So I'm going from 4, 3, 2, 1 to 0. Okay, so can we put something in standard form? Yes, hopefully. All right. Shouldn't be anything brand new for us. Coefficients. If I asked you what are the coefficients of each of the terms, would you be able to give them to me? Hopefully. So coefficients are the constant values of each term. So the numbers that are not ever changing. So your coefficient of this monomial would be a 3. Your coefficient here would be negative 2. Your coefficient would be 5. Your coefficient here would be negative 1. Your coefficient here would be 7. Okay, so we got terms. We got them writing in standard form. We've got coefficients of each of the terms. So it's your constant value for each term, the number in front of the variable. What would be the degree of this 7 right here? 0, right? Because there is no x. X to the 0 is just 1. so it'll make it go away. All right, so we got coefficients, leading term. Remember, your leading term is the highest degreed monomial in a polynomial. So the leading term in this case would be 5x to the fourth, which would make my leading coefficient positive 5. Okay. All right, and then your constant term is the number without a variable. So in this case, my constant term is the 7. Okay, so given a polynomial, we hopefully can figure out the degrees of each term, 3, 2, 4, 1, 0. I can then rearrange them in standard form. So put the highest to the smallest. I can identify the leading term, I can identify the leading coefficient, I can identify the constant, and I can identify the coefficients of all the other terms. We can do that. It's nothing brand new in our lives. Okay, so let's talk about the graph behavior of all these graphs. Again, this should be hopefully reviewed since we've kind of talked about odd and even graphs before. We're going to just jump into a little bit more detail-wise today. So we're going to talk about what happens when we have a degree of 2, a degree of 3, 4, 5, 6, and then 7. And what does a rough sketch of each of those look like? So we already talked about quadratic, right? So quadratic, we know that that graph is going to be a parabola that is concave up. It was just x squared. So I guess I should make this actually be consistent with that. So let's make it have a 0, 0 vertex. What does it look like for a degree of 3?
Can I go see the mirrors?
Yes. Let me give. But where things get a little bit crazy, or interesting, I guess, not really crazy, is this middle chunk. As your degrees get higher and you have other things happening to your polynomials, you're going to have some interesting things happening in the center of your function. Now, for now, they just have one term, so they're not going to really be any different. It's when we start adding other terms to it where the interesting components start to happen. Okay? All right, so given a polynomial with the highest degree, you should be able to tell me what the end behavior is. And then what would happen if I made all the a's negative? They would just switch, right? All your evens would go down, and all your odds would switch sides. Do I need to go through any of that? You got that? Okay. All right, so we've got our behaviors for all of our different polynomials. All right. I don't think we need to go through the leading coefficient. So don't put this in your notes, just let's make sure we got this, right? So if my highest degree is even and our A is positive, my end behavior is up and up, right? And then if it is negative, then my end behavior is down to down. Yeah? And then if it's odd, oops, do I not have the odd ones? There's my odd one. If my highest degree is odd and my A is positive, my left behavior is going down to infinity, up to positive infinity. And if it was even, then it was negative, then positive, or positive and then negative, if I'm saying it right. We've got our end behaviors down. I feel like we do. And then all that notation that's in there. Okay, so go ahead and get your calculator in hand. We're going to use our graphing calculator to make a quick sketch of this polynomial function. And we're going to introduce a new concept, which is turning points. All right, so on your graphing calculator, we're going to type in negative x to the third. Get my calculator out. Oops. So negative, make sure this is the negative button and not the subtraction button. Negative x to the third plus 2x squared plus x plus 1. zoom 6 just to get to a standard 10 by 10. All right, we getting something that looks like that? Yeah? Good. You finished? Nice work.
No, it's fine.
+1. All right, so we've got that graph in front of you. Oops, let me get my PowerPoint back up. So what are we asked for? We're asked for what our n is. What's our highest degree for this function? This is a degree of 3. What is our leading coefficient, or our leading term? What is a of our highest degree? -1. Thank you. All right, so as x approaches positive infinity, so as my x is going to the right, what's happening to our graph? What's happening to our y? Is it going all the way up or is it going all the way down? It's going down, right? Which makes sense because my a is negative. So it's going down to negative infinity. And then on our left, as x is going all the way to the left to negative infinity, what's happening to my y? It should be going up. But remember, whenever we're in odds, it's going to be opposite of each other. Now, here's a new concept. Turning points. How many turning points are on our graph? Yeah, there's 2 turning points, right? So let me just flip back over here to a second. Where's my calculator? So if we look at our calculator, turning points is where we change from decreasing to increasing or increasing to decreasing. So I have a turning point occurring here, and I have a turning point occurring here. So we've got 2 turning points happening in our function. And that is there for a specific purpose. So there's a rule that says that you can have at most, I'm just going to do a little sidebar here. You can have at most n minus 1 turning points. So since my degree was 3, I can have at most 2 turning points, which in this case I do have all 2 of them. I could have 1 turning point 2 in a cubic function. Okay? But at most, n minus 1 turning points. So if I had a degree of 4, then I could have at most 3 turning points. If I had my highest degree was 5, I could have at most 4 turning points.
Why is my graph background green?
I don't know.
Huh.
We'll have to play around with that then. I'm sure there's some way to change that. Okay? All right, so can you get this in graphing on your calculator? Everybody's able to do that? Yeah? We can determine the degree, the leading coefficient, the end behavior, and now we're adding in this new concept of turning points. So looking at the graph, being able to analyze that. All right, so let's go ahead and do a second one. Let's do x to the 4th minus 3x to the 3rd plus 2x. Go ahead and graph that in your graphing calculator.
Oh, there, I found it.
You fixed it?
Yeah.
Oh, I forgot to sketch the last one. You getting something that looks like that? Roughly, sketch-wise, yeah? All right, so if that is my graph, make this on here so it's on the video. So rough sketch of it. So we got this happening, this happening. It's even worse than the first one, but that's okay. All right, so we got something happening like this. Hopefully your sketch looks a little bit better than mine. So my highest degree n, in this case, is 4. My leading coefficient is 1. As x is going to positive infinity, my y is going to positive infinity. As x is approaching negative infinity, my y is also approaching positive infinity. How many turning points do we have here? 3. Good. All right, so turning point, turning point, turning point.
Turning points where they change.
Where the change is from decreasing to increasing.
Oh, I think we covered that before, right?
Yeah, because they're kind of like absolute maxes and mins. Or not absolute, relative maxes and mins, right? Okay, so now we're just calling them turning points. Okay, so given a polynomial function, can you describe the leading coefficient, the degree, the end behavior, and turning points? And can you graph it on your graphing calculator? You can do all those things? Okay, so now we're going to move into the world of multiplicity and the zeros. So we remember that zeros are points where that crosses the x-axis, so your x-intercepts. We can all find zeros on our calculator. Yes, because you had one on your quiz. So finding zeros on our calculator, hopefully we can do. And remember I introduced the word multiplicity last week or whenever it was. Do you guys remember what that was when I said multiplicity? Remember we talked about quadratics. So a quadratic needs to have 2 solutions because it has a degree of 2. If I can spell solutions. There we go. So if you had 2 solutions here, there are your 2 solutions. But what if we had a discriminant that was equal to 0? Then we only had 1 solution. So what had to have happened there for us to have 2 solutions? It needed to occur twice, right? So it has a multiplicity of 2. Well, that's going to occur often when you get into higher degree polynomials because you might have more things happening. Okay, so zeros of a polynomial function. So here we have the turning points thing if you want to get that written down. So the graph, we already have it written down potentially. So we know that the graph of f is going to have at most n minus 1 turning points. So if you didn't write that yet, you might want to write that. And we know that the function is going to have at most n real zeros. So if my degree is 4, I can have at most 4 real solutions. If my n was 5, I could have at most 5 real solutions. My degree was 6, I can have at most 6 real solutions. Now let's think about this though. If my degree was 5, so if n is 5, I could have 5 real solutions. What other combos could I have? Could I have 4 real solutions and 1 imaginary solution? Think back to our complex conjugate. What always happens with imaginaries, they've always got a buddy partnered up with them. So I can't have a combo of 4 and 1, but I could have a combo of 3 real and 2 non-real. Right? I could have that combination. If I jump down to 2, could I do 2 real, 3 non-real? No, can't do that. Could I do 1 real and 4 non-reals? That's a potential, right? We could have 1 real and 4 non-real solutions. Okay, so these are my only combos that I have available if my degree was 5. Out of these 5 real solutions, some of them could be repeats of each other, and you could have multiplicities of them happening more than once, and that's okay. I could have 1 solution and it happening 5 times. That would work, okay? But I could only have 5 real solutions, 3 real solutions with 2 non-reals, or 1 real with 4 non-reals, okay? So you have to remember, if you have imaginary solutions, they are always partnered up with the conjugate, right? Don't forget that component. All right, is everybody good with this part? Okay, let me know if I'm moving too fast. Okay, so if a polynomial function has a factor that is repeated, these duplicate roots are labeled as a multiplicity of n. So if we have repeated factors, whatever the degree is on that repeated factor is going to be its multiplicity. Okay, so if a polynomial function has a factor that is repeated, these duplicate roots are labeled as a multiplicity of n. And that n is whatever the degree is on that. Okay, so for example, I think this is the example in the next slide. If you had f of x is equal to x plus 3 cubed times x minus 1 squared as your polynomial function, what would be the zeros? Well, your zero of this linear factor would be negative 3. So we would have a 0 of negative 3 with a multiplicity, I don't know why I put it in parentheses, with a multiplicity of 3. And then I have a 0 or a root of positive 1, and that would have a multiplicity of 2. Okay. So if we can get it to factored form, you should hopefully be able to find your roots or your solutions. And if any of those linear factor forms are repeated, so this one's repeated 3 times, this one's repeated twice, then you would have multiplicities to go with them. Okay? So given a polynomial function, we can find leading term, leading to highest degree, end behavior, turning points. We can graph it on our calculator. We can do the zeros on our calculator, right? And now, if we can get it into factored form, we should be able to then solve any polynomial equation, hopefully. We can get it to factored form, or if we can get it to something of a quadratic form, then we can use any of our quadratic solving methods. So completing the square, quadratic formula, or square root property. Okay, so we're going to end here with a few solving polynomials. So let's see if we can do it. So find all real zeros and state the multiplicity of repeated zeros. So we got y equals 2x to the 5th plus 8x to the 4th minus 154x to the 3rd. So we need to solve for our zeros, which means we're just going to set this equal to 0. Solve for x. So the first thing I always check to do is, can I factor anything out of that? Can I factor out 5, thanks. I was going to say, do I have it not in standard form? Thanks, good catch. Do I have a GCF, a greatest common factor? Can I take a 2 out of 2, 8 and 154? Yeah. My smallest degree x is x to the 3rd, so I'm going to factor out a 2x to the 3rd, which leaves me with x squared plus 4x minus 77. 2 goes into 15, 7, 1. 2 goes into 14, 77. It's equal to 0. Okay. Can I factor this? Are there any factors of 77 that get me to 4? 77 divided by 7 and 11? No, but yeah, 7 and 11? Yeah. So negative 77 would be 11 and negative 7. My leading coefficient's 1. So this factors to x plus 11, x minus 7. Bring down that original 2x to the 3rd is equal to 0. Okay, so I have it in factored form. So what are my zeros? going to start here first. My 0 here is going to be a positive 7. We got an x is equal to 7. I got a negative 11. What's my 0 here to the 2x to the third? 0. Whenever you have a monomial in front, it's always going to be 0. But since it's happening 3 times, it has a multiplicity of 3. So there would be all 5 of your real solutions. I got 1, I got 2, and then I got 3 zeros happening. So total's 5. So this should always total 5, no matter where you're going. Okay? So we're good with that one? All right, let's try another one. X to the 4th minus 4x to the 3rd plus 4x squared. So I'm going to set it equal to 0. X to the 4th minus 4x to the 3rd plus 4x squared. Can we factor anything out? X squared, I like that idea. If I take out an x squared, I'm left with x squared minus 4x plus 4 is equal to 0. Is that factorable? Are there any factors of positive 4 to get to 4? My only factors of 4 are 1 and 4. That adds up to 5. Or 2 and 2. That adds up to 4. So that works. But to make it negative 4, I'm going to make both of them negative. So this factors to x minus 2, x minus 2, x squared, which is just x squared times x minus 2 squared. Condense it. So my solutions are x equals 0. That has a multiplicity of 2. And positive 2, which also has a multiplicity of 2. Again, your solutions should total up the highest degree, even if some of them incorporate imaginary solutions, non-real. Alrighty. Here we have 4 terms, so probably can't factor our normal way with the trinomial. So here we have 2x to the 3rd plus 6x squared minus 5x minus 15 is equal to 0. Do I have a GCF that I can factor out of all those? I do not. So I can't factor out a GCF. I can't factor a trinomial. So do you guys remember doing factoring by grouping last year in Algebra 2? So whenever you have a group of 3, if you have 3 terms, you just factor like you would factor a trinomial. If you have 4 terms, you try to factor by grouping. And grouping is you group the first 2 together or the last 2 together. And you are more than welcome to rearrange any of these terms to make it work out. But I have a feeling that it's going to work out this way, the way we have it. So if I just group the first 2 together and pull out the GCF of the 2x to the 3rd and the 6x squared, well, the GCF of 2 and 6 is a 2. The GCF of x to the 3rd and x squared is x squared. So then that leaves me with x plus 3 inside my parentheses. If I group the last 2 together, my GCF of negative 5 and negative 15 is a negative 5. And the rule of thumb is if this is always a negative, take out a negative, because I need it to be positive inside. So that gives me x plus 3 left over. Now, because these linear, or I guess in this case they are linear, they might not always be, because what's left inside my parentheses is exactly the same, I can then take my GCFs that I pulled out, combine them together as a factor. And then take the common stuff inside the parentheses and set that by itself. Because if you think about it, distributive property-wise, you would take the first term of 2x squared and multiply it by the x plus the 3, which is what's happening right here. Then you would take the negative 5 and multiply it times the x plus 3, which is happening here. So you're just kind of doing the reverse of the distributive property. Okay, so now I have it in factored form. Now I should be able to come up with my solutions. This one's easy. That's negative 3. This one's not quite as easy. We've got to do a little bit of solving. So if I set that 2x squared minus 5 equal to 0, that gets me 2x squared is equal to 5, which gets me x squared is equal to 5/2. How do we undo a square? Square root both sides. So I get plus or minus the square root of 5 over the square root of 2. How do I rationalize that? Multiply by square root 2, top and bottom. So root 10 over 2. So my solutions are negative 3, negative square root 10 over 2, and positive root 10 over 2. Yeah?
I just have a question.
Sure.
So because there's 2x plus 3, would, like, when we simplify and bring it all together, would it be x plus 3 squared?
No, because you're doing the reverse of the distributive property. So it's the 2x squared is being multiplied to the x plus 3, and then the negative 5 is being multiplied to the x plus 3. So it's kind of just combining them together like the reverse of the distributive property. So if I took this, I would take 2x squared and multiply it by the x plus 3, which is what we have written here. Then I would take negative 5 and multiply it to the x plus 3, which is here. Good question. Okay. All right. Moving along. Next one, 12t to the 4th minus 5t squared minus 2 is equal to 0. All right, so because we had the highest degree of 4 and then 2 and then 0, I'm going to try to factor it like I normally would, just keeping in mind that instead of t, I would have t squared. So 12 times negative 2 is negative 24. Factors of negative 24, that would get me to negative 5, would be negative 8 and 3. Yeah, that gets me negative 5. Gets me negative 24. My leading coefficient is 12, so I'm going to put them over 12 and reduce. So I can take out a 4, so negative 2/3. Take out a 3, 1/4. So this is going to factor to 3t squared minus 2 and 4t squared plus 1 is equal to 0. Okay, so zero product property tells me this is going to be equal to 0. So I'm just going to jump right to t squared is equal to 2/3. Add 2, divide by 3. The other one's going to go to t squared is equal to negative 1/4. Subtract 1, divide by 4. So now when I square root top and bottom, rationalizing this, multiply by square root of 3, gets me t is equal to plus or minus root 6 over 3. Same thing on the other side, square rooting top and bottom. Here we're going to get an imaginary solution. The square root of negative 1 is I. The square root of 4 is 2. So we get t is equal to plus or minus I over 2, or half an I. So my 4 solutions are negative root 6 over 3, positive root 6 over 3, negative I divided by 2, and positive I divided by 2. My highest degree is 4. So here I had at most 4 real, but I only had 2 reals, which means I had to have had 2 imaginaries. Okay. All right, so solving polynomial equations by regular factoring, factoring by grouping when we have more than 3. So if you have 4 terms, try to factor by grouping. If you have the 4-2 combo, then just make it 2 squared. If this would have been 6 and 3, instead of t squared, what would it have been? So if this would have been a 6, can I erase this? Is everybody okay? If this would have been 6 and 3, then it would have been, now I don't even remember what it was. What was it? It was 3, it would be 3t cubed minus 2 and 4t cubed plus 1. And then it would have been t cubed is equal to 2/3 and t cubed is equal to negative 1/4. And then we would cube root both sides. That's a bad cube root. Right? We can take the cube root of a negative, so you would have all real solutions. Okay, so we got solving polynomials. I kind of jumped over this, so let's jump back to this. So one other thing to add on to multiplicities is when you get to calculus next year, that's where you end up going, you're going to have to be able to sketch graphs by use of no calculator. So multiplicities tell us, 1, how many times a 0 occurs. So if there's any repeated zeros. But it also tells us a little bit of information about what that graph is going to look like. So if your f has a real 0c that has an odd multiplicity, so the multiplicity is 3 or 5 or 7. That would be a bit crazy if you had a multiplicity of 7. But if it did, if it had an odd multiplicity, then we know that that graph is going to cross the x-axis at whatever that 0 is. Okay, if it was an even multiplicity, then it doesn't cross it. I like to call it that it kisses it. Okay, it just touches the x-axis at whatever that 0 would be. Okay. So why does this matter? So if we had something like x minus 3 squared times x plus 4 cubed, and I needed to do a rough graph of this, well, I know I'm going to have x-intercepts at positive 3 and negative 4, right? What would be my end behavior? Is this an even or an odd graph, first and foremost? It's odd, right? Because my degrees are 2 and 3, so that would make my highest degree 5 if I multiplied it out. So we know it's odd. Would my leading coefficient be positive or negative if I multiplied it out? Be positive, right? Because there's no negative here, there's no negative there. So my end behavior of an odd positive is down and then up, right? We're down on the left, up on the right. So then at negative 4, because I have an odd multiplicity, that means it's going to be crossing over my x-axis, right? So it's going to be going like this, and then it's going to start coming down. At this next one, it's just going to kiss it, so just touch it, and then come back up. So my graph would probably look something like this. I'm not quite sure where this relative max would be. I'm not quite sure where my y-intercept would be. I could figure that out by multiplying it through. But this would give you kind of a rough idea of what it would look like. Okay, so if you have an odd multiplicity, you know that your graph is going to be crossing the x-axis at that point. If it was an even, then we know that it's just going to kiss it. Just kind of some extra food for thought when you're thinking about graphing. So you're going to be doing a lot of non-calculator work next year. Okay, so we got polynomials. We got the graphs of the polynomials, depending on the multiplicities. Only last thing I want you guys to get down in your notes. Do you guys remember your sum and difference of cubes formulas? So if you had a cubed plus b cubed, how do you factor that? Do you remember that formula? You cube root the a and the b to a plus b. And then to get the second trinomial, you square the a, so a squared. You square the b, so b squared. And then that middle term is always going to be opposite in sign. So if this is positive, that's a negative. And then you multiply your a and b together, so ab. So if you had to ever factor a sum of cubes, that's what it would factor to. This 0, you should easily come up with your solution here. This guy over here will not be factorable, so you're going to have to either complete the square on it or use the quadratic formula to solve this quadratic, or whatever it may end up with. And if it was subtraction, then it would be a minus b, a squared, opposite in sign, so it starts out as a negative, so it's going to be a plus, a times b plus b squared. This is always a plus because you're squaring your b, so it always will be positive. Again, you can easily come up with your solution from this. This will not be factorable, so you'll have to use the quadratic formula or complete the square on it. Okay? All right, once you have that written down, go ahead and jump to your laptops if you could, please.